Yeah. Actually, the angle is a little bit twisted, so
Oh,
it's fine.
don't worry about completely up. Oh, yeah.
Oh yeah, I think it's fine. If you're right between, it's still fine. It's just
Yeah,
don't
yeah,
bother.
I see.
Eh,
Okay, cool. Oh, so I actually have more board space.
yeah.
Okay, perfect. I might even. Okay. Good.
Great. So today we're very happy to have Nick, who just joined us this fall as a postdoc. He's going to tell us about applications of machine learning for studying the S matrix. So yeah, take it away.
Thanks, Theo. All right. Yeah, so as Theo mentioned, I'm Nick. I'm a new postdoc in the amplitudes group. I did my graduate work with JJ Carrasca at Northwestern, and I've been enjoying the LA weather. So it's already cold in Chicago, so I'm happy to be here. All right. So as the title suggests, this is a reference to something that's kind of been a big buzz in the media recently, which is transformer networks, which will underlie a lot of these language models that have been deployed at industry scale. And so really, this story is a story about I would say a nascent program of applying machine learning techniques to understanding quantum field theory by way of the S matrix. All right. So what I'm going to kind of lay out today is some things that I've been thinking about over the past year and some kind of early stage and mid stage projects that are kind of in the works, and how we're going to get at this question of how we can leverage these statistical techniques of machine learning to understand things about analytic structure in quantum field theory. Okay. So good. So I'll just briefly kind of go through how we normally think about the interplay of these two games for people that are not amplitudes people in the audience. So normally we want to understand objects in quantum field theory and their observables. We understand them through their amplitudes. And what the amplitudes community tries to do is essentially extract information about quantum field theories by better understanding their on-shell observables. Okay, so typically the pipeline, at least that I'm most familiar with, is one where we take understand on-shell structures and use that to inform insights about the underlying quantum fields. And so typically, if you're an amplitudologist like me, you don't think so much about Lagrangians and fields. You think a lot more about on-shell degrees of freedom and the particle content. You try to reverse engineer the observables directly from the functions that are relevant on-shell. And so the way this works is, rather than thinking about Lagrangians, you say, okay, well, if I have some loop amplitude, I know that I can construct it from some basis of integrals that are determined by the perturbative structure of the S matrix. And so as I go to higher and higher loop order, I get integrals of higher transcendental weight, and I fix these things using principles of generalized unitarity and on-shell constraints, right? What I spent my PhD thinking about was playing the same game, but for EFTs, where rather than looking at higher orders in loops, we look at higher orders in the effective coupling and try to understand how those Wilson coefficients are constrained based on on-shell principles. So the general game is you have some amplitude, you know it's constructed from a bunch of rational operators. You can sum over the center of mass energy S squared, or center of mass energy squared, to some higher order in the effective coupling. You have some Wilson coefficients, C sub n, and there's some angular dependence depending on the multiplicity object. And I'm just going to, this is just a rough heuristic. Obviously, there's much more complexity stored in these Wilson coefficients than simply single objects in terms of the effective coupling. But the general game here is that you want to understand to the extent to which EFTs are constrained in terms of the Wilson coefficients by imposing on-shell constraints. So a classic example of this is one that I know Nicolas and others in the crowd are familiar with: positivity constraints from unitarity and causality, where you can bound Wilson coefficients by directly imposing on-shell principles. What I was more focused on in my PhD was using some of these newer on-shell properties like color kinematics to understand the extent to which gravitational engaged theory amplitudes are constrained using these on-shell constraints. But just to give you a sense of scale, where are the bottlenecks in these research programs? The bottlenecks are hidden in the fact that these free coefficients and these kinematic functions explode in complexity as you go to higher and higher order in perturbation theory. So just to give you a sense of, where's my color chalk? So to give you a sense of scale, it's routine that as you start getting to the state of the art in these calculations, the number of free coefficients in these EFT amplitudes goes anywhere from 850,000 terms to even, I think the largest expression that the largest calculation we worked with was on the order of 4.5 million terms, which starts getting very, very close to some of the very, very high loop amplitudes that complexity, the high loop amplitudes that you would see in some of these past work and others in the room.
So what operator dimensions did you go
Say it again.
in?
Alpha prime to the 12. So, yeah, so mass dimension m to the 12 or m to the 24, right? And there's a whole story why we actually cared about going this high in the EFT expansion. We wanted to look at resummations, and we actually need to get good perturbative data. I won't go into that. I'm happy to talk offline about that. But just to give you a sense of what the scale is, if I have 850,000 terms up to the order of millions, just inverting this matrix requires 10 gigabytes to even terabytes worth of RAM. Okay. And so you're not running this on a computer, you're not running this on your laptop, you're sending this off to the cluster and asking it to kind of crank through these expressions for you and build out the matrix and try to simplify it down to a concise form that you can actually read. Okay. Good. All right. And so this is all just to say that a lot of the state-of-the-art calculations in scattering amplitudes, and this is no exception with EFTs, this is especially true at loop level, demand you to have a command over very large data sets and perform the calculation as efficiently as possible to push the next frontier. Okay. So in parallel, while this program has been developed over the past 20 to 30 to 40 years, there's been a program happening in machine learning. I would say also kind of got its start in the mid-'80s, right around when Park Taylor wrote down their first expression for gluon scattering. So developments in ML, which also deals with large data sets and extracting insights from these large data sets, has been happening in parallel. So just to give you kind of a timeline, the first kind of what I would call modern day neural networks, so multi-layer perceptrons and stochastic neural nets were both around the mid-'80s. And I point these out because this is precisely what the Nobel Prize was awarded for this past year in physics. All right. So we have, I mean, John Hopfield is an honest computer scientist or honest physicist, but there are this parallel program that touches lots of data and has been able to do incredible calculations and extract insights from this data that has been kind of operating in the background, at least parallel to our field. And I guess the question that this kind of research program wants to answer is, can we start leveraging some of these two tools that seem very parallel to the types of techniques that we utilize to leverage to extract more insights from the field? Okay. And so I will say that a lot of these big developments since the '80s have been primarily in industry applications, in computer vision, and in natural language processing, which were dominated for, I'd say, 10 years to 20 years by a class of neural networks known as convolutional neural networks and recurrent neural networks. And both of these were usurped in the past 5 years by something known as a transformer. Okay. So now all of the state-of-the-art calculations in computer vision, natural language processing are essentially just done with these transformer networks. And so the whole point of this talk is just to kind of lay the groundwork of how these objects, which we'll define, can allow us to potentially extract insights about these data points relevant in analytic calculations for QFT. Good. All right, so let me just lay out some goals for the program. So I should emphasize that until last year at this time, this was my entire research program. It was just kind of applying the kind of standard amplitudes toolkit to extract analytic insights about amplitudes to inform what we know about QFTs. And so right now, this field is very much in its infancy, but I think it's reasonable to kind of bound what goals look like. So I think back to like my first couple of years as a PhD, and it took me a while to convince myself that generalized unitarity was much better than finding rules, right? And so I say that just because it's when I want to define success of what we should be actually aiming for, just reproducing the calculations that we already know how to do shouldn't be the bar, right? So if this is going to be useful, we should hold ourselves to the threshold of saying, well, let's actually either get to the state of the art or push past it, or work some like hybrid form between machine learning techniques and what we already know how to do. And so the goals, I think, should be to develop new tools that push the state of the art to either streamline the calculations we already know how to do so that maybe we can then push our current techniques even further than we already can. And then lastly, and ideally, elucidate hidden structures that we don't already know about, right? So more than just kind of continuing to push the frontier on very developed and mature research programs, in an ideal world, using these tools actually can allow us to learn new things. And I will say that there's a paper that has come out recently that has made a step, at least, to potentially doing this. Okay. All right. And this is a Blackboard talk, so you guys have any questions, feel free to kind of speak up. All right, so now let's just define what exactly do I mean by machine learning, and what are the tools we're actually going to be using to potentially extract analytic insight. Is everything at this point clear?
The comparison what all these experimentalists are doing when like looking for like hidden signals and like some huge data piles.
Yeah.
Like what are they also using transformer networks, or are they using some other?
They are definitely using neural networks. Enrico brings up a good point. A lot of these machine learning techniques have been employed for almost decades now in the experimental community. And a lot of what they're using them for, so a great example of this is at CERN, where to get better statistics, they have to throw out lots of superfluous data that are not Higgs signals, right? So to actually identify the Higgs, you have limited bandwidth in what you're allowed to collect. And so you need to do some pre-processing of the data, know how many signals you threw out, and try not to throw out as many Higgs events as possible, right? You want to collect all the Higgs events. And this is a perfect application of these neural networks where you can do effectively a categorization model where you say, this is most likely to be a Higgs event, we'll keep it and we'll analyze in the data. And this is all the stuff that we threw out as background. We might be missing Higgs events, but if I can quantify the type 1 and type 2 errors of this model, then I can run better statistics on it. So it's the same underlying mechanism under the hood, but the way that we are going to leverage it for analytic insights can be very, very different. Okay. Okay. So what are we talking about? So ML is just statistics, but the way it's been used recently in a lot of these deep learning algorithms is it's statistics in a completely different parameter regime than we're told to use statistics in our like undergraduate and graduate courses. Okay, so what is the normal story of statistics? You say, I have some task. I give you some, so given some data set, X1, X2, XM. I have some sample data that has M data points, and X of I is drawn from some distribution with dimension D. And my job is to train a model that has parameters drawn from RP, such that my model takes in some X of I, given these parameters that I'm going to tune or train or fit to my data, and I'm going to get some output. That's the entire game. The entire game is I have some parameters to define my model space, and I want to use data to constrain these parameters. And so the normal game is, I'm going to go over here. The normal game is what we are familiar with, which is we look in regimes where the number of parameters in my model are much, much less than the dimensionality of the space and the number of data points that I've sampled. Okay, so let me just give a classic example of this. I have some sample space, and I have a bunch of data points, and I want to draw a trend line. And my job is to fit some linear model while minimizing errors across those data points. Okay. And so you can see number of parameters to define this line, 2 parameters, a bunch of data points far exceeds the amount of information I need to actually constrain this model. Okay. So this, I would say, works really, really well when we have some known function space. In other words, we understand the formalism that defines the physics or defines the underlying dynamics of the system. And moreover, the data or the model space is low dimensional. In other words, I can give it to a grad student and they can identify what the relevant functions are, and that model can then determine the relevant dynamics of the system. So like the standard model has on the order of 20 or so free parameters. That is what I would call sufficiently small, right? Since I have many, many more particle events that I'm collecting at the LHC. Okay, so what I would say like modern or deep learning techniques do is they turn this paradigm on its head, and they say, well, let's consider model building in this very funny parameter regime where P is either on order or much, much larger than the dimension of my data and the number of points that I've sampled. Okay. And already you might say that sounds very, very weird because why do we like this parameter regime? It's because we don't overfit our data, right? If I have more parameters than I have data points and all these parameters are linearly independent of one another, I'm going to have full capacity to fit every single data point in my system. And so even though it will have very, very little bias. It won't be very robust. Because as soon as I add a new data point, it could be very, very far away from this overfit model. And so where this is actually really relevant is not where I know the relevant dimensions of my system and they're all linearly independent, but it's where I don't know the function space, so unknown function space. And in principle, very high dimensional data. And I would say oftentimes these two things are one and the same. So like a classic example of this would be like jet physics data, where you're operating in some non-perturbative regime, your perturbative understanding of QCD breaks down, and so you don't really have a good understanding of what parton led to which jet, right? Or theories of models of turbulence might be a good example as well, where in principle you have everything you need to constrain the model, but in certain parameter regimes, your kind of ability to capture the relevant length scales breaks down in these turbulent regimes, and you might have a better chance using some machine learning model where the dimensions are not independent but are actually broadly overlapping. Okay, so what's a good example of this? The classic example that comes from computer vision, where you have some pixelated data, and you're asked to say, well, is this picture a dog, or is it a cat? And I don't yet have an effective field theory that tells me whether something's a dog or a cat. And I certainly don't know the model space, and I certainly don't know how many dimensions there are to being a cat or being dog-like, right? But absent understanding the function space, I can feed it to some neural network, and it can tell me, oh yes, this kind of looks like a dog, but if I add bad whiskers, this kind of looks like a cat, right? Good. Okay, so this is a killer app of machine learning where I don't have independent dimensions, but they are broadly overlapping my neural net, and I get to train the neural net in a way that learns this model in a data-driven way. Okay. Good. Okay, so I think I'm doing well on time. So I've said the word neural net without actually defining what a neural net is. So let me just write this down. Okay, so it took me a while when I first kind of started exploring the literature, like using my understanding of the language you use in physics to decode a lot of the jargon that's in the CS literature. So oftentimes when you look at kind of papers with neural networks, they'll have like these very funny kind of diagrams that look like this. And when you see it, you're like, ah, yes, that's a neural net, obviously, because that's the image that I've seen in the literature. And so I just kind of want to say briefly what all these lines mean and what all these dots mean, and kind of frame it in terms of what we're very comfortable with, which is these affine transformations and linear models. Okay, so if I were to write down an expression for this model over some d-dimensional space with some bias parameter b, I would just say, oh, my model is some linear transformation of lambda of x that looks like m x plus b. And m and b I know are free parameters that I get to constrain with data. Okay, and I might set up some quadratic loss function and minimize along r squared and fit these to the data points that I've sampled. Okay. So all this is if I have some input vector that then maps to some output vector. Okay, so when you see one of these layers, literally just think of a linear transformation. just some rotation and shift. Okay. Good. And so all this is it says, well, I don't know what the relevant dimensions of my data are, so I'm going to just add nonlinearities to the system. Okay. And so all this is it's just some affine transformation that goes into a nonlinear function. So I have lambda of sigma of lambda of sigma, and that eats up some input data, and all the sigmas are just nonlinear functions that are known as activation functions. So if I were to plot sigma as a function of x, rather than being some linear function, when x is negative, it would look something like this. When x is positive, it then activates. Okay, so there's a bunch of these kind of different expressions that are relevant for different reasons. But going forward, just think of all of the models that I'm going to draw, these big black boxes, as a combination of linear transformations and these nonlinear functions just concatenated together. Okay, they're just stacked on top of each other. Okay, and it turns out that by having the most kind of primitive nonlinear model that you could think of, you can encode incredibly robust predictions about data that you don't have an understanding of the function space for. Okay. Yeah.
Some fixed function or
Yes, good. Okay, good. Yeah, so I've drawn sigma in red because sigma does not change. Okay, sigma is not a parameter in your model that you're tuning. Everything that you're tuning is in blue. All right, so all these linear transformations, these matrices, that's the only thing I'm tuning. In fact, that is like precisely the reason this is at all a tractable approach to problem solving, because you can parallelize the optimization problem, sending it back through all these linear systems. But the nonlinear units themselves are completely fixed. And my question is just, how do I rotate the signal in just the right way to give me some kind of very general function space?
So if you use different sigma, then they will eventually give you the same result.
If I used it, yeah, so
You build different model.
yeah. There's like all of these theorems about neural nets being universal function approximators, and you just need one type of nonlinear unit. You don't need to, yeah. So exactly, yeah, that's right. Good. And so the whole name of the game when trying to find better models and better network architectures is what is the most efficient way to get these to be as universal as universal as possible. Right. So, what do we need from machine learning to start doing some of this high dimensional data analysis? We need some trainable architecture, which in this case would just be the neural net. We need some metric of success, so some loss or reward function. And we need an optimization algorithm. And all of this is just given to you. All right, it's already coded in some Python library, and you don't have to touch any of this. All right, you get to just choose. The stuff that we provide is the data. Okay, so I'd say these are the 4 ingredients, and the stuff that we would provide trying to solve problems in particle physics is data that is representative of the problem we're trying to solve. Good. All right. Background. All right, so why should I have any reason to believe that machine learning and deep learning and all these kind of fancy buzzwords is going to do anything for analytic calculations in particle physics? Okay. Good. So I'll just start here. I'll start by giving not the most compelling answers, but they're important answers because they allow us to actually extract data. So why ML, why can that inform analytic calculations in scattering amplitudes? One, as I kind of mentioned in the intro, we have lots of very large data sets that we can easily generate. And moreover, many of the problems that obscure state-of-the-art calculations in particle physics have nothing to do with the physics, have nothing to do with our understanding of the model. It has to do with like silly, like intermediate expression explosions, where because of the combinatoric nature of perturbative data, you eventually get to this point where even if the expression that you get from your algorithm is small, reducing it down to something that's useful, that intermediate step can be really, really bad. All right. And so I'll call that process the process of simplification, but really it's a combinatoric problem where kind of the optimal way of distilling the important physics has an unknown model space. And a priori, it's very high dimensional. Okay. Good. But as I said, I don't think these are the most compelling reasons to think that this has any chance of working. The most compelling reason is because everything we work with in extracting analytic expressions from particle physics models and applying our algorithm of choice, it's all sequential symbolic data. And so it's very well suited for the types of problems that the natural language processing community has been doing for the past 10 to 20 years. Okay.
Is there some classifying, like, is there something that classifying whether something is an amplitude or it's not? Let's say I give you an expression of an amplitude and I flip one sign of this random term, then it's not an amplitude anymore.
Sure.
Can I have a classifier that tells me that that thing now is not an amplitude anymore, high probability or not?
Sure. Yeah. I mean, right now, if you flipped one sign in a gigabyte file, I would have no way of knowing. But if you can make it, I mean, all these files can be machine readable. So you could just try to train some network to identify valid amplitude expressions. Now, obviously, what you would...
Like I should have a machine learning to check whether your ancillary files are correct.
Yeah, now, I mean, what you would need, I mean, really, this isn't like some catch-all, right? I mean, you need lots of data, right? Like the data essentially needs to uniquely determine the problem space. And we'll talk about the types of problems that you could actually hope to solve with this. But the data needs to be representative of the problem you're trying to solve.
You're going to give a couple examples of some papers that have been written?
Yeah.
Clifford and Myers.
Yeah. I'll go through those and some other stuff that we've been working on for the past few months. Okay. All right. So
is there something that tells you that, with enough great parameters, this convolution that you wrote down will converge to, something that you want?
So in general, no, but there are principles that you can use to say this is how many parameters I need to actually get as close as possible to the minimum loss function, like minimum value for the loss function. So like there are actually, as physicists have started playing more games with machine learning, they've started seeing that a lot of these models that you would think are black boxes have a lot of very clear structure that can inform questions like that. So I'll mention that in this section. Okay. All right. So as Steve mentioned, there's been some very nice papers in the past couple of years, and especially in the past few months, that essentially do two types of tasks. So two tasks. What are the tasks that we care about a lot, or some tasks that we care about in scattering amplitudes research that are well suited for NLP? One, simplifying expressions. So the idea is if I have some, what is the analog in natural language processing? If I have some book, I want to distill it down to a paragraph, and I want to distill that paragraph down to a sentence, and I want to preserve as much meaning as possible. How do I do that? And so very similarly, you could imagine there's been a paper recently with Cliff and Matt, and their PhD, Matt's PhD student, that has done this game for spinor helicity. And this is, I think, related to a paper that came out in 22, where they did a similar kind of simplification game for polylogs, which are the types of functions that you get post-integration for perturbative calculations and scattering amplitude. So there are already kind of games like this in literature, and I can provide archive numbers if you guys want to look. But the second one is the task of fill in the blank. And this is the game that I've played the most with, just because I had the opportunity to fortunately watch Lance and some of his collaborators from Meta in Wisconsin play a game with symbols where they used terms in the symbol alphabet to predict the integer coefficients using these transformer networks. So what am I talking about when I say fill in the blank tasks? So I'll just say Lance and collaborators at Meta in Wisconsin had a game for fill in the blank for symbol multi-loop symbols. Good. So let me just make this more concrete. So imagine I give you some sentence and I say something to the effect of the largest planet in our solar system is like, and everyone says Jupiter. Good. All right. So you can also play a different game where you say, well, rather than just having one word, you leave two blanks. Okay, so you have the blank planet in the solar system is blank. Obviously, largest and Jupiter is still a valid pair, but you also have things like the smallest planet is Mercury, right? Or the water-ist planet is Earth, or something to that effect, right? And this is, okay, what does this have to do with amplitudes? What it has to do with amplitudes is that there are parts of the expression in a full amplitude that are simpler to solve for than the entire function. So you can imagine if I have some three-loop amplitude or 4 point n equals 8, I know that if I want to use general unitarity, the easiest terms to account for are the maximum cuts because they're uniquely determined. There's no ambiguity. I can't shuffle contact terms around. I just write down the cubic graphs and it's done, right? So I have stuff that looks like this. I have stuff that looks like this. But then as I go to higher orders, I start getting expressions that have ambiguity about where I put the contact terms. Okay, so you can imagine if I have some like S and T channel expression, do I put the contact term on the S channel or do I put the contact term on the T channel? Right, and there's lots of ambiguity that goes into that. And what I would love to be able to do is just say, can I just give it the maximum cuts and then train it to populate the rest of the expression with all the contact diagrams. And this is very similar in spirit to what Lance and his collaborators did for the symbol, where they said, I have all these things that are completely constrained by dihedral symmetry. I can fix those no problem. I want to teach the transformer to populate the rest of the expression. Okay. And so it turns out that, and we'll get into why this is the case, but these types of fill in the blank with the token that's missing is a classic language processing archetype that is really, really good for amplitudes if you can figure out how to train the right model.
Do you have enough data to train it? Like for this particular theory, can you train it with any theory? Like if I give it a 3-loop amplitude of whatever, some Young-Mills theory, or like some scalar theory, like can you use that as training data, or do you need the data from that particular theory that you're talking about?
So if you give it data from n=8, it's going to learn n=8. So I mean, I guess you could imagine building different models for different theories. But the games that we've played to like pretty good success is at tree level, where because of generalized gauge freedom, you have a huge parameter space of different contact terms that you can train the model on. And the way that carries up to higher multiplicity is kind of invariant. You start learning similar expressions because it turns out that contact terms really only care about their local behavior. But yeah, I say that most of these methods right now are theory dependent. Okay. All right. Okay, so what's the pipeline? Pipeline is, as I said, you find some data, you find a way to create as much data as possible so that it's representative of the problem you're trying to solve, and then you just feed it to this transformer network. So let me just, what's the idea here? So think of these blocks just like the nonlinear units that I told you about at the beginning, but they have kind of special properties going on inside of them. Okay, so I have this layer called a tokenizer. I have this layer that called an embedder. I have this magic layer called a transformer. And then I de-embed and I de-tokenize. Okay, so what goes in is just sequential data. Okay, so let me give an example, a very, very silly example of very simple scalar theory contact term. So if I have some amplitude, just has an S channel U minus T over S. Okay, I can treat the division as like a verb, almost like an operator, and I can turn this into some sequential object where the division comes first, it goes U minus T and then S, right? And then my job is to turn that into a sequence of numbers. So division's one number. So I have some map where I have division, that goes to 1. I have some dictionary for U, T, and S. I send it through my tokenizer, which just decodes it in numbers. So this becomes 1, 2, 5, 3, 4. All right. So I have some vector that just encoded in numbers. And then all this layer does is it just embeds it in some vector space. Okay. So this embeds it in some vector space. I pass it, which is now some matrix X input that has the sequence length and the dimension of that vector space. I send it through this transformer. It does all the clever manipulations of that neural networks like to do. I get some output, X out, that's usually normalized to be similar to a probability distribution. I send it back to a sequence, and in this task, let's say I was trying to take this S-channel object and say, is the contact term, does it have plus or minus one? And so all this model does for a living is it takes the S-channel object and it predicts what is the contact term that I want to address that with. Okay. Good. And so in the process of training, I take this prediction and I compare it to the output data, which is the truth, which let's say it was +1. So if I had it as +1, it'd be a valid guess. If I had it as -1, it'd be an invalid guess. And then if it was right or if it was wrong, I would backpropagate that information and try to tune the model. Okay. And so I'd say the most interesting kind of information theoretic aspect of how this training happens is what the loss function actually is. So if you think way back to like your undergrad stats class, the loss functions usually you take like ax equals ax minus b, you're trying to solve some linear system, you square that so that it's positive definite, and you try to minimize that along some quadratic loss function. The loss function here is completely different. So loss function we usually use in these language tasks is something called the cross entropy loss, which is a very, very complicated word to describe something very simple, which is you compare the probability distribution of the truth, which is always some delta function because you know precisely what you want, to the probability distribution that is guessed by the transformer network. So if I go to this intermediate step, all of these vectors are just probability distributions over the token space. And so the cross entropy loss, it just takes the truth, P true, the prediction, Q prediction, and it sums over all entries of P sub I log of Q sub I. Or graphically, the idea is that if I have some distribution, the truth might look like some delta function where I know that it's exactly +1. But the guess from the machine might be something that looks like this. And given the bin that has the highest probability predicted by the machine, it'll say, I want to select that. I guess in this case, it would be something higher probability over here, and we would have had a wrong answer. Okay. And so once I have this predicted distribution versus the true distribution, I can just plug this into the entropy loss function. And this is minimized precisely when Q goes to P. All right, so the closer I get to delta function predictions, the better and better my model gets. That's all it's doing. If you like, all these transformers do for a living, they just predict conditional probability distribution. So the more data you give it in a sequence, the better it gets at predicting the final outcome. Okay. And this actually is a really cool expression because it actually allows you to understand the limits of what your model is actually going to be able to learn. Okay. So what do I mean by that? So principles and limitations. So let's talk about some kind of general expectations for what you might expect when you actually do the training process. So I'm just going to draw some of the plots we have from this contact term game. Okay. Good. So Principles. And limitations of these models. And in understanding what the limitations are, you'll see very clearly the types of problems that are really well suited for this, and the types of problems that you're only ever going to get approximate solutions for. Okay. So, what does the training process actually look like? And moreover, how do you answer the question, how much data do I need? And two, how big is the model? In other words, how many parameters do I want to encode in my neural network to actually get to pass a certain threshold of predictive accuracy? Okay. And while I can't answer this from the outset, I can tell you that if you train on 3 different models, you can effectively predict how far down the loss function will go. Okay. So roughly speaking, if I have some average loss during the training process, and I plot this over the number of data as measured in gigabytes, what you'll find is that the more data I give it, the final average loss of the model will go down in a straight line as plotted on a log-log plot. Right, so this is really just a power law. All right. So roughly speaking, if I go 1 order of magnitude up in tokens that's been trained on, it'll go 1 order of magnitude down in the loss function.
Anything that you can do with the slope? Like, can you plug in physics or some information to make that slope steeper?
So this is like a big research question of whether this is like an intrinsic slope that's attached to model training, or if it depends on the architecture. If like different architectures will give you different slopes for this power law. Okay. But you can just play this game. You can, you can start very early. Like if you start at like 1,000 or 10,000 different examples on the order of megabytes, you'll start to see this trend line. Okay, and this is, to be clear, this is the final loss for the final epoch. All right, so the average loss over the final epoch after it's done training. And similarly, you can take H bar, which is right there, and plot it over the number of parameters in your model. And you'll get a similar downward trend that's determined by some power law. And I should say here, assume that parameters are held fixed and tokens trained on are held fixed as well. Okay. But the way this pops up in training is if I look at H as a function of H bar as a function of compute. So compute as measured in floating point operations, but really just think of this as time. So given the capacity of your computer to train through cycles or to crank through floating point operations, over time, what does this training curve look like? What does the loss function look like over time as you're training the model? Okay. And obviously, compute is really just a function of the parameters. You have more parameters, more floating point operations, more data, more floating point operations. So think of this as like a function of these 2 objects. What this ends up looking like so 100 megabytes, 1 gigabyte, 10 gigabytes. It looks something like this. So that's the characteristic loss curve where you get some decay. This is still, I should say this is still log. So as I add, so this is for, let's put this up. So this is a curve of more parameters, fewer parameters, and it goes down fixed data. Okay. And so then, say add more data. You'll see is that there's this line that is known as the compute optimal training curve, right? So it's the maximum amount of compute or maximum amount of the minimum loss that you can get for minimum compute, right? And you might ask yourself, as I wrap up, well, great. So you're telling me if I just throw all the computing resources in Hoffman at this thing, I'll get a perfect amplitude predictor, right? Because it just seems to go down forever in perpetuity. But if you think about it, what is this thing doing? This loss function is predicting probability distributions of the data set, right? And we know that natural language, much like symbolic data in scattering amplitudes, have some intrinsic entropy. In other words, I don't just get to say, given this, I know this is the next term, and I know this is the next term, and I know this is the next term. So if I had zero entropy, I would know exactly what every other object was given the input, right? For some types of problems, that's absolutely the case, right? So for constraining master integrals, I know that given an integral, I have a very specific coefficient. But generally speaking, amplitudes have gauge freedom. And so as a result of that gauge freedom, there is redundancy built into the data. And so just because I have a S-channel graph here, I don't necessarily have to address it with a contact term here. I could put it over to some T-channel graph or some U-channel graph. And so there's ambiguity built into the data set. And that's precisely what allows me to train, right? There is a multi-dimensional model landscape that I actually get to train the model on. And as a result, the entropy as a function of the number of parameters and the number of tokens that I train it on will look something like some constants. A2. So these are the power laws, some fixed point, and then some intrinsic entropy of the data set. And the way that you measure the intrinsic entropy of the data set is you just look at, given all the input sequences, what are the valid output sequences? So if as I feed the model longer sequences, the entropy of that output will go down. But if I have only one input, so like let's say I just had a single diagram and I wanted to populate the entire rest of the expression, that would be a very high entropy problem that I had to solve because there's many terms that could come next. And so as a result, this H naught will be very large. And so the general problem solving principle here is that if you want this to be as predictive as possible, you want to have your sequence length as large as possible given some finite compute, right? So we've been playing these games, and just as a rough heuristic, if you look at the kind of the examples and papers that are out there, they usually cap it at about 1,000 tokens in a sequence. And that gives you kind of large, pretty good predictive power, but it's also computable. You can actually just run it on a cluster and it will run in finite time. Okay, so I'll just wrap up. So I just want to wrap up by saying that this is a very nascent research program. And right now, the beginnings are very humble. And I don't mean to say, I don't even think that these types of techniques, they are not supposed to supplant all of the stuff that we've been doing for the past 20 years, or I've not been doing. The field's been doing for the past 20 years. They're supposed to potentially augment our current tools and allow us to push further and ideally extract new insights hidden in these symbolic structures. And so if I think of the papers that are out there, the papers that I mentioned in the talk are the only papers that are out there on this topic. All right, so in the scattering amplitudes community, which is a few hundred people strong, there's the paper from the Harvard group. A recent paper from the Slack group with Meta in Wisconsin. And then the recent paper from Cliff and Matt, simplifying spin helicity expressions. And so if you want to do an exhaustive literature search, this is it, right? And so there's lots of low-hanging fruit. There's lots of problems that are waiting to be solved. And just to kind of name a few, this past summer, or spring into last summer, we're exploring how to construct double copy representations directly from Feynman rules by teaching the model to use generalized gauge freedom to start with a gauge invariant object and transform it to a gauge invariant object that's also in a color dual representation. I mentioned the contact term from Max Cut's game. So present and future, I hope to do a bunch of stuff with you guys and my collaborators at UCLA. So I'll take your questions now. Thanks.
The double copy representation.
Yeah.
What kind of examples do you have?
Well, they're all tree level, all for like simple scalar theories. So right now,
And you have like, it generates new things. You have like new examples of things that hadn't been done before. Or
no, so not yet.
not yet.
Yeah. So yeah. So right now we're working on that. Yeah. So right now, the setup is similar to what I described. I say, actually, if I were to think of the two types of tasks that you could use these transformers for, this is much more similar in spirit to the simplifying spin helicity expressions and simplifying polylogs, where you start with some base form and then you scramble it, right? So what's the base form? The base form is a valid color dual rep, and then you scramble it with a bunch of choices of generalized gauge freedom. You get a bunch of things that are valid amplitudes, but are not valid color dual representations. And so by teaching the model to go from these valid expressions or these gauge invariant expressions and biasing it towards selecting out BCGA representations, right now we can produce terms that we already knew existed, right? And so the next hope is you start generalizing some of these expressions to higher multiplicity and to loop level.
But it can de-scramble something. You take something, scramble it in a completely different way. It learns how to de-scramble it.
Yes.
Or you actually do know the output.
Yeah. And so it learns how to, it's very similar in spirit to applying Schouten identities.
So given that you tokenize the whatever expression you're looking at into some sort of like sequential list of numbers using whatever library, how do you know, or how do you ensure rather that this cross entropy loss function does not depend on the choice of library if there's like a numerical value assigned?
Oh, it absolutely depends on the choice of library.
Oh, okay.
Yeah, absolutely. Yeah. So if you chose, and actually choosing different libraries to sequence the same data type is like, I think, a really interesting research problem, where you can imagine saying, we've been exploring some of this these past few weeks, where there's a question of, well, there's lots of different ways to tokenize this data, right? Do I want to, I'll just say the analog in natural language processing is, if I have some large text, do I tokenize the letters, Do I tokenize the words? Do I tokenize the syllables? Do I tokenize entire sentences? Right, so the trade-off here is that the larger your token library, the smaller the sequences, but obviously the larger the dimension of your token library, the closer things are in like your embedding space, and so it's kind of hard to differentiate between them. So you're trying to find this perfect alignment between sequence length and token size. But for every different tokenization, the loss function absolutely changes.
Sorry, I was just gonna follow up. So for these types of projects, do we just tokenize every single intricate detail, or do we go like, oh, this is a rational function versus the polylog versus whatever? Like, to what resolution or like coarse grading do we use?
So a good heuristic that, or what I have found, it's better to take the objects that you know are important. So if you know a polylog is really important, just tokenize that polylog. Don't tokenize the polylog with all the integers and all the division factors. Just say that polylog expression is a token, and I want to see if where that polylog appears in the sequence. But there's a hierarchy of different tokenizations, and that's up to you to determine.
It's kind of funny, right? Because at the beginning you started out with like you want to be like as generic as possible, right? That's the whole game. And now you're feeding in structure again, which like in your thing of like, oh, the old school whatever statistics thing fitting the line,
Yeah,
versus the like making your parameter space insanely large to fit every possibility or like many possibilities. And now it's like there's some trade-off, and again, it's how it seems.
yeah, you're trying to find like this intermediate region where once you've identified like the minimal set of information you can give it, it'll learn much more quickly.
So for this token, is it known what ChatGPT would do? Like,
So I think it's reported that like the current version of GPT-4 is like 350,000 tokens. Is that what you're asking?
yes.
Yeah, so they tokenize by syllables. So like ing is its own token. Yeah.
It's very tailored to the English language. Yeah.
No, but then they also have things for different languages as well. I mean, they've done translation tasks and yeah. And you can start, you can start playing funny games where you ask ChatGPT to like translate text to video. Like it's doing a mapping between video tokens and language tokens, and I mean there's like a whole, it's kind of like a Tower of Babel sort of thing where, But anyway, yeah.
One very naive question, but if you train this network, I mean, ChatGPT, for example, sometimes says wrong things, right? What can make you 100% sure that whatever the new terms gives you are indeed correct?
So yeah, good. So I'd say an important, it's important to make sure that you can easily verify if the final answer is a valid expression. So with these types of symbolic expressions, the way that you verify, you just plug in floating point numbers.
All right.
So if I have some very complicated expression, I go to Mathematica, I assign some replacement rules, I give arbitrary numbers. If I have like, 10-digit precision, I'm pretty sure it's a valid expression. But in principle, there's no, I mean, you can kind of imagine that all of these symbolic expressions, they're discrete graphs, and you have valid moves where you can move between the graphs, and some parts of the graphs are, gauge equivalent, if you will. And there's no reason to believe that you wouldn't fall out of that subcategory. And so you do have to check that what you have is a valid expression. Yeah.
Similarly related question, I don't know if this is in connection with like what they do at CERN, but there you have to have a kind of figure of merit to determine what events we're considering as signal here.
Mhm.
Do we do something similar here where we're saying we have to do a calculation to determine not only what probability of being an actual amplitude this is, but also like compare it against like things we know are not going to be amplitudes? Again, I'm not sure.
No, yeah, I see what you're saying. I mean, what they're doing at CERN, looking at experimental signals, you have to be able to quantify very accurately your type 1 versus type 2 error for the model, because that actually feeds into your statistics. Here, the rule of thumb is that the data you feed it is going to determine what it's giving you, right? So if you feed it a bunch of data that only ever has gauge invariant expressions, it's likely only going to throw out or spit out gauge invariant expressions. So the data you feed it is really defining the model landscape, and it's just creating the best approximation of that model landscape as possible. I don't know if that answered your question, but
I think so. I guess, you know, related, do you also feed your model like background that is like things we know are not gonna be in amplitudes?
oh. I've not done that, but that'd be interesting. If you could,
Why would you do that? I mean, isn't that like feeding it garbage?
well, I guess
So,
you
like,
could,
Why would you feed it garbage? Like if you.
but you could, yeah, go on. I mean, you could imagine. There's different ways you can do this training. I mean, all I've outlined here is a very specific type of unsupervised learning where you have inputs and outputs kind of already specified. But there's reinforcement learning schemes where you try to make the model as robust as possible and you give it kind of false data and then tell it, oh, by the way, that was false data. Right now, this is just in a very specific learning paradigm. Yeah.
Let's think, Nick, we can do this.